So far, we have found out what steady state looks like when it is stable, and in the last video, we looked at what the economy looks like once you have attained steady state, i.e., that small k and small y don't grow, and capital K and capital Y grow at the rate of small n, that is population growth, which means that in the long run, your per worker income cannot really grow. It will reach stagnation after a point. In this video, we study transitional dynamics. As the heading might suggest, you're studying transitions, which means you're studying transitions to steady state. So we're going to look at what the economy looks like before you have reached steady state. So you know that before you reach steady state, if you're to the left of the steady state, then small k is increasing because net investment is positive. So you have the standard diagram here. So if you're here, and this is to the left of the steady state, there is positive growth. So from K1 you go to K2, then you go to K3, so on and so forth. Now, there's something you should probably notice right away from this diagram, which is that this growth is actually slowing down, and eventually it's going to look really, really small. And this is something you can eyeball from this diagram. And this slowdown necessarily occurs because of this concave shape of the FK curve, which in turn obviously comes from the concavity of FK itself. So notionally or intuitively, you might think that the growth rate of small k is slowing down as you're reaching the steady state. To verify this intuition, I'll first look at the Cobb-Douglas f of k and show that this intuition is indeed correct. And then I'll in fact rigorously prove this as well. So we are trying to find out. The question here needs to be very clear. I think you need to ask questions very clearly in order to be able to answer them. The question here is then, is growth rate of small k slowing down? What is the growth rate of gk? We know is small k dot by k. This then is equal to sfk minus n plus delta k by k. So that's equal to SFK by K minus N plus delta. So for a given small k, this is the growth rate of small k. For the Cobb-Douglas case, you have Gk equals S K alpha by K minus N plus delta, which is equal to S by K1 minus alpha minus N plus delta. 1 minus alpha is positive, right? Which means this whole thing is positively sort of shaped. So as K goes up, Gk goes down. And this is something you can observe from here. Because when K goes up, your denominator is larger. And you can probably verify this because dgk dk is equal to S alpha minus 1 K alpha minus 2, and this is negative since alpha is between 0 and 1, obviously. So the intuition which you get from this diagram is indeed correct. Before I prove this rigorously, there's another diagram which I think we should look at, which is going to make things even simpler. So you have Gk equals to S by K to the power 1 minus alpha minus N plus delta. Let's disaggregate this into component 1 and component 2. So as a function of k, this is of course a horizontal line. So you have, this is just n plus delta, the horizontal line. This is this component 1. What does it look like? It looks like this. Okay, and the reason is, so let's just suppose alpha was 0 or 0.5, and then you'd get this, right? And this does indeed look like this. The way to verify this is dgk dk negative, you know, and d squared gk by dk by dk square is, as you know, s alpha minus 1 alpha minus 2 k alpha minus 3, and this is positive, right? Which means your slope is increasing, and this is a convex downward sloping function, which is what we have graphed here. So this is s by k to the power 1 minus alpha. So for a given k, this vertical distance between this and this is the growth rate. So if you're here, then this, if at k1, this is the growth rate, right? This gap. When you're at a higher k, say k2, this is the growth, and it's smaller than what it was at k1. So this is just a verification and a diagram which in fact is quite useful and relevant. Let's prove this now for the general case. Is it really true, or is it just true for the Cobb-Douglas function? And you saw that when you looked at this diagram or at this diagram, this decrease in growth rate is being caused by the curvature here of s by k1 minus alpha, here of sfk. And we know that fk's curvature is that it's a concave function, right? And this is by assumptions made on the Solowian extensive form production function. So the proof probably has something to do with the curvature of f of k, and you can probably try it yourself before you take a look at this. All right, so g of k is equal to s fk by k minus n plus delta. The intuition is, you know, average falls for concave functions. Okay, you know this, and this is the average, and this falls, you know. And so the best example, of course, of this is the average cost function. When you assume increasing marginal costs, i.e. that the cost function is convex, average cost keeps rising, because marginally the amount of money required to produce an additional unit of output keeps increasing, so average cost keeps increasing. This is intuitively something you know. For a concave function, it's obviously the opposite. That is why average product of labor usually falls for a concave production function. Nevertheless, we will prove this rigorously. Okay, so dgk by dk is then equal to s k f dash k minus f of k by k square. Okay, so just consider the numerator. The denominator is positive anyway. Right? Okay. So, by assumption on f, we showed that f double dash k is negative, which implies that f dash k is decreasing, right? We also know f of 0 equals 0. All right, therefore f of k is equal to integral from 0 to k f dash t dt. You need to look at this expression really carefully. You know, based on how a definite integral is defined, that this is equal to f of k minus f of 0, which is equal to f of k. That's the first thing. This is by definition of a definite integral. The second thing you must note here is that k here is fixed on the right hand side. The function is defined as a function of t. K is fixed. It's a given value, right? It's not a variable. Okay. Now, you know that f dash t is decreasing, right? Since f dash is decreasing, right, f dash k is less than f dash t for all t in this range, right? Because because k is greater than all of these t's. So the value that f dash takes at k must be lower than the values it has taken before that. So f of k is greater than equal to, if I just take this as f dash k dt, and this in turn is just equal to k minus 0 f dash k is equal to k f dash k. This is slightly complicated, and understand, once you replace the f dash t with f dash k, because this is principally true, this can just be written as f dash k into 0 to k 1 dt, and you know that the integral of 1 is just t, and then when you put in the upper and lower bound, you'll just get k, right? Now, you might still have doubts about how we jumped to this step. Understand why. Look at an integral. If you have x and f of x, so f of just y, just and suppose this is f of x, and suppose f of x is just greater than some other function g of x, then for any x, the area under g of x must be lower. So I would be able to write that 0 to t, 0 to z f of x dx is greater than equal to 0 to z g of x dx. We have done something similar here, but with a constant function which is equal to f dash k. Alright, okay. So, since f of k greater than equal to k f dash k, obviously dgk dk becomes negative, right? Because this numerator then becomes negative. So this is the rigorous proof for how growth rate in capital per worker falls as capital per worker rises. And again, if you look at this, which is what we had originally, this whole thing is convex and downward sloping, and this is something we just showed. So this component 1 looks like this, and this component looks like this. And so again, for a low level of k, growth rate is massive. For a higher level of k, growth rate is really very small. So this is the major point behind transitional dynamics. So all right. So you know small y is equal to f of k, right? And this fact means that as the growth in k slows down, the growth in small y is also going to slow down. And We're going to prove this rigorously again, probably in a problem set. But let's look at this for the Cobb-Douglas production function. So suppose this is k alpha. So y dot by y is equal to alpha k dot by k. So gy is equal to alpha gk. When k goes up, gk goes down, implies gy also goes down. Let's look at the aggregate variables then. Capital K is small k into L, which implies that g of capital K equals to g of small k plus g of L, which is equal to g of small k plus n. So again, as small k goes up and we approach the steady state, g of small k goes down, which implies g of capital K also goes down because this doesn't change. Similarly for capital Y. What is the set of diagrams then that we get? First, and this is something we started in the last lecture, so we might want to take a look at that. So if this is TSS, and in the last video we showed that beyond this is going to become flat, but before that you see that growth falls over time, which means that the slope of this is going to continue to get flatter and flatter until it approaches 0. So the graphs look like this, and you can see that the slopes are falling, it's becoming flatter, it's a concave curve, so to speak. Similarly for capital K and capital Y, you know that eventually they're going to continue to grow at rate n, but you see that the growth rates of capital K and capital L are also continuously falling, which means this is what it looks like. What happens then to our comparative statics results? In the last video we saw that a change in S has only level effects but no growth effect. So let's look at an economy once which was in steady state, and now S changes, and what happens in that transition, so to speak. And this is something we have shown already, right? So you're originally at steady state, ln y, ln k. So originally you're at steady state, you've reached steady state and you have got 0 growth. Then t change in S, this is when small s changes, which means now you're off the steady state again. So to look at it using our standard diagram, you're here, but now this increases, which means relative to the new steady state, you're off. The old steady state is equal to small k1, but it's now before the new steady state, and so the old curve just becomes irrelevant now. So now you're just at a point below to the left of the new steady state, or for all practical purposes just the steady state of the system you're now in. So you're once again going to get growth until you once again reach the steady state, and again it becomes flat, right? I think the diagrams for capital K and capital Y can be constructed by you based on what we have done thus far. Finally, we'll look at our transitional dynamics diagram again and look at the same answer on that diagram. So you have small k, this is n plus delta, this is SFK by k. You're here, you're at the steady state value when the two are equal. Now S has risen. So you go here, this is S new Fk by K. So at this old level of the steady state, you now have positive growth again, and you go on and on and on till you reach this point, and growth continues to slow down until you reach the new steady state, right? So the point is, again, even when small s increases, that gives you an initial fillip to economic growth per worker, sure, but that growth peters out because of the concavity inherent in your production function, and once again you eventually reach a new steady state and growth rate becomes zero. But this is again the level effect clearly visible, and this is the fact that there is no growth effect.